thanks for inviting us to talk and for your interest. Yeah, I'm just going to give a real quick overview on what we did very recently, just last month, basically the entire month of September and a few days in October, taking measurements from a C-130 from Fairbanks, Alaska, out over the sea ice. And the field experiment was called ARISE, Arctic Radiation Icebridge Sea and Ice Experiment. And our main objective basically was to collect a data set from the C-130 that we could use to help better understand the relationship between the changes in Arctic sea ice and the regional energy budget as influenced by clouds. So if you go to the next slide, please. The basic problem is that while we understand to a certain degree the positive feedback on Arctic warming that sea ice reduction has, this is due to the reduction in the solar reflectance or the increase in solar absorption by the ocean in areas that are now ice-free in the summertime. So we sort of understand that fairly well, but we really don't understand the role of clouds under these changing conditions. In other words, are cloud conditions changing, and do these changes, and do the clouds enhance or offset the impact of decreasing sea ice on the radiation budget? So, of course, we have satellites that are measuring surface and atmospheric conditions, including sea ice, clouds, and radiation over the Arctic all of the time, but owing to a lot of different factors, the complexity of the Arctic atmosphere, the complexity of the surface, and the general lack of observations, the measurements that we make from satellites are somewhat uncertain at times and therefore difficult to interpret. And that's where an airborne science experiment like ARISE can really help. So next slide. Of course, we can't answer the big picture questions with an aircraft data set, at least with 1 month of measurements, but we need and we have satellites that and hopefully models that can do that for us. But we need to use our airborne assets like the C-130 here to collect data that we can use to test and improve our satellite measurements and to provide information that are difficult to measure or are not available from satellites at all. So the next slide, please. Oh, well, that's a picture of the C-130 in case you hadn't seen it. It's a pretty new asset to NASA. I think this is only the second field campaign that it's flown in, and we made a lot of modifications and added a lot of instrumentation to it for this mission, which I'll talk about in just a second. So next slide. Basic high-level objectives for ARISE were to go out and, from the C-130, measure the spectral and broadband radiative flux profiles in the vicinity of clouds, quantify surface characteristics, cloud properties, and other atmospheric state parameters to the extent that we could, and to do this under a variety of Arctic atmospheric and surface conditions, including over the open water, the sea ice, and land ice, and, of course, coinciding with satellite overpasses as much as possible. And then the second major objective was to acquire detailed measurements of land and sea ice characteristics to help fulfill the NASA Operation Icebridge mission objectives. So this is a joint mission between the Radiation Sciences program at NASA and the Cryospheric Sciences program, as well as the Airborne Sciences program. Next slide, please. This is a picture of the C-130 just before we left for Fairbanks, fully instrumented. We basically turned it into an airborne radiometer with in situ probes and a laser altimeter to characterize surface atmosphere, cloud conditions, and radiative effects. So we had a set of broadband and spectral shortwave and longwave radiometers looking up and down to measure radiation and also to infer cloud properties and surface characteristics. We had a wingtip probe to measure the atmospheric state, including 3D winds. We had the Elvis laser altimeter to characterize sea and land ice properties. We had a set of cloud probes to sample the clouds in situ, and we had a really nice digital camera system mounted in the belly of the aircraft as well. Next slide. So these next two slides basically just provide a list of the various instruments with a lot more detail, and also the principal investigators are listed here. I'm not going to go through these, but I included them in the slides in case people wanted to refer back to them at any time. Next slide. And the next slide. Okay, this is a good one. So this is just a list summarizing our sampling strategy, or the types of profiles that we flew. Basically, we wanted to fly specific flight lines over the sea ice for Icebridge. These tended to be high-altitude surveys with the laser altimeter. So we flew repeat lines from previous campaigns, and also new lines to support our radiation experiments, and also to characterize the sea ice across the marginal ice zone. And we tried to repeat these when we could during the ARISE measurement period. We developed and conducted a number of grid box experiments these were primarily to help validate Ceres, which is our NASA satellite that's measuring the radiation budget at the top of the atmosphere, and also inferring surface radiative fluxes using a variety of different data sources as inputs. So the idea here was to go out and map radiative fluxes from the C-130 at the top of the atmosphere, or basically the altitude ceiling of the aircraft, which is only about 22,000 feet or so. And also to do that mapping very close to the surface, as close to the surface as we could get, which was usually around 500 to 1,000 feet. And we did this over a wide range of Arctic surface conditions, including the open ocean, broken sea ice, more concentrated sea ice. And at the same time, we acquired other data, sampling clouds in situ, making measurements of ice properties and atmospheric state. And these could all be used to help test the inputs into the series algorithms that are being used to help better understand the cloud radiative effects in the Arctic. The other thing we did was we did very focused low cloud experiments where we flew profiles above and below low clouds. These were radiative closure studies. We flew above and below low clouds and then sampled the clouds in situ. And these will be used to test retrievals both from satellite and from the aircraft radiometers. And we did some surface albedo experiments, trying to measure the surface albedo in diffuse versus skies over different surfaces, and test our ability to compute the top of atmosphere albedo, which is important in the series inversions and such. Next slide, please. So let's see, this is slide 9, I think, yeah. So this slide illustrates the covers that we obtained from the Elvis, the laser altimeter. Okay, here it is. So the red and the black lines show all of the areas that Elvis acquired surface data, and the red lines are the high altitude lines where a swath of data were collected, since the Elvis has the ability to scan. So these are areas where up to like a 1.7 kilometer swath of data were obtained. So you can see how, you know, the covers that we were able to get during ARISE, and a large data set, you know, was acquired over variable ice conditions across the marginal ice zone. We had one long transect that you can see there that extended along the 140 line all the way to 82 north. That was in mostly clear conditions. And we had a really nice underflight of Cryosat-2 on another day. Next slide. This is just a illustration of some of the variety of sea ice conditions that we encountered, just a few of the images that I pulled off out of the archive here. From, you know, the broken ice pack that we encountered north of 80 degrees, scattered conditions to the south while the ice pack was still melting early in our campaign, and then, of course, the ice started to freeze while we were out there, or refreeze. And so you can see some of the black ice and the ice milk that we encountered. And all of these, of course, have different radiative impacts, which we were able to measure. Next slide. So I guess the next few slides provide some examples of some of the radiation experiments that we conducted, which you guys might not be as interested in, but I'll just rip through them real quickly here. This first one is just an example of a grid box experiment that we conducted for Ceres, where we mapped the radiation in these like 100 to 200 kilometer regions. And these were typically centered around solar noon, where we had lots of coincident satellite overpasses by Ceres and by other instruments on Aqua, Terra, the SUMI MPP satellite, MEDOP, etc. So during one of these experiments, when we were out flying, this grid box for 2 or 3 hours, we had as many as 6 Ceres overpasses while we were out there. And one of the Ceres instruments on Terra, we were able to program to scan through regions, do special scanning to increase the sampling. So these target areas were actually pre-selected, so we could pre-program one of the instruments. Next slide, please. This is our flight track during what will probably be one of our golden days for this grid box experiment, but real briefly, this just shows the mapping pattern being flown in red at the time that the A train was passing through the area. The planned flight track is in yellow. So we usually anchored one of the legs of these grid box experiments to fly directly under the A train, which has Ceres and Modus on Aqua in formation with CloudSat and Calypso satellites, for example. They provide 3D cloud and aerosol structure, which we can use in our data analyses. Next slide. And this is an example of one of our radiative closure experiments. This will probably also be one of our golden days for low cloud radiative closure studies. In this case, we flew out over the ice sheet and flew back and forth across the ice edge, making measurements above and below a low cloud deck, and then porpoising through the cloud to make cloud microphysical measurements. Next slide. I'm going to skip this. This is just an illustration of more details regarding that particular radiative closure study. We came up with a name for these. We called them radiation sandwiches. Sometimes they're called radiation wall patterns. We did a number of these during the course of the experiment. Next slide. This is just a quick summary of all of our flight tracks during the mission, overlaid on top of an AMSR-2 sea ice concentration image that was taken towards the end of the flight. So we concentrated a lot of our effort, on that tongue of ice that extends to the south, off to the east, north of the Canadian coast, just because it was reachable for our aircraft and we could get out over the ice and make, a few hours of detailed measurements. We got 17 flights completed before we started having trouble with the airplane, but it really acquired a really good data set while we were out there. By the way, I should note that all of our science reports for all of these flights are available on the ARISE page on the Earth Science Project Office's webpage. The link is there at the bottom. Next slide. I'll try and finish up here. Just some mission highlights. From my perspective, we had 17 science flights. As I said, we conducted about 150 hours of flying. We had 6 grid box experiments for Ceres. We obtained numerous sea ice lines for Icebridge and to correspond with our radiation experiments and studies. We also got data over some Alaskan glaciers. We were out there, during the transition from melting to freezing again, so that was pretty neat. We observed that sea ice transition and characterized the wide range of sea ice conditions and associated cloud and radiative effects that went with them. The low clouds that we encounter were geometrically and optically thin, as most people already know they are out there, particularly over the ice. They're often multi-layered and often extended right to the surface. We encountered a lot of fog, which was impossible to get below. We did conduct a number of focused low cloud radiative closure experiments. We also observed a lot of haze, which we weren't really expecting. There's been field experiments designed actually to go out and measure that where they haven't found it. We weren't really, didn't have the instrumentation to observe it in detail, but we did encounter it. We think, anyway, visually anyway, the haze was there. We conducted a first ever melt season underflight of Cryosat-2 with the Elvis, And we got a really nice calibration flight for our radiometers right before we came home. So next slide. We did conduct a variety of education outreach activities that were a lot of fun. A number of the links and some of the information for those are provided here, courtesy of Christy. Next slide. And finally, the last slide here, I'll just note that the instrument teams are now, of course, in the process of calibrating and reducing their data sets. So we don't have a lot of results available yet, but all of the data will be available by April of next year. And we've got a comprehensive data management plan, which we will soon be making available as well. It'll probably be signed off this week or next. And that'll also be distributed and made available on the Earth Science Project Office website. So that's all I had to say. If anyone has any questions, please fire away. And again, thanks for inviting us to talk.
Okay, thank you very much. It's Martin. Are there any questions for the ARISE team?
This is Paulo. Just a comment. I don't think there's an actual standard term for milk ice. It could be probably sugar, or if it's more developed, gray white. So it'll be interesting to find out, what stage of development is what you saw. But it's probably sugar, like lumps of spongy ice that look like milk. But there's no actual as milk ice.
Okay, yeah, sorry about that. I'm not a sea ice person, really. That was just sort of the term that we came up with when we were in the field for it. I'm sure there is a more official term for it from the sea ice community, but thanks for pointing that out.
Sure. I'm sure if we saw photographs of it, we'd be able to tell better what it was, how it formed. It sounds like it might just be slush on the water surface.
We did actually share that picture with Jackie Richter-Menge while we were in the field. She gave us a nice, good summary of what she thought it was, what processes created that.
Yeah, my guess is sugar, but it'd be good to know how quickly it developed. What's the stage of development in terms of age.
Yeah.
All right. Thanks.
Any other questions? Okay. If there are no more questions, then I'm going to conclude the meeting.